So, now let us continue on and look at the Schottky contact. So, we saw that there are two kinds of contacts that are formed in metal semiconductor junctions. The first is the Schottky contact, which is which we call the rectifying contact, but we really did not say why it is rectifying, and the second is the ohmic contact. And what we will do now is first take the Schottky contact as our object to study, okay. And we will always consider the Schottky and ohmic contacts for the n type semiconductor. And what we would like to do is firstly study the electrostatics, okay. So, we will study the electrostatics of the junction and then look at the current voltage characteristics. We will then take the material out of equilibrium and study the current voltage characteristics. And from these two we will effectively try to develop a small signal impedance model for the device, okay. So, this is the first of the semiconductor devices, and by going through this analysis we will be in a position to then repeat this analysis for other devices. So, just to revise, just to look at the Schottky contact again, you have a metal and you have a n type semiconductor. So, this is your n type semiconductor, and we already saw that the Fermi levels will align, the semiconductor will give electrons to the metal because your phi m is greater than phi s, okay, and this is an n type semiconductor. So, the electrons will move into the metal and the conduction band will bend away from the Fermi levels, and this will be the band bending diagram, okay. So, what we are trying to find out here is we are trying to solve out for the exact nature of the variation of this bending. How does the energy bands bend in space, what are the electric fields in this region, what is the potential in this region, what is the charge in this region, etc., etc. So, that is the objective of our study, and that is what we mean by the study of electrostatics. So, if you think of this region, we already discussed that the electrons are not encouraged to exist here because this region has given up some electrons to the metal, plus and it has resulted in the bands bending in this particular manner, which encourages electrons to roll downhill and stay away and keep away from this region. So, if you want to think about it in terms of looking at EC minus EF, okay, which is basically that difference, then EC minus EF here is very large, and therefore, the electron count, which is n is equal to NC e to the power minus EC minus EF by kT is very small, and therefore, the electron population in this region very close to the junction is quite small, okay. So, since this EC minus EF is greater than the EC minus EF in the bulk, the electron population here is much smaller than the electron population in the bulk. So, you should remember that the population scales exponentially with the energies. So, small differences in energies lead to large differences in carrier concentrations, and kT is not a very large number. So, I mean it is kT by Q is of the order of 25 millivolts, and kT is therefore about 25 milli electron volts. So, it is not a very large number. So, this region has got very few holes because holes are the minority carriers in the n type semiconductor, and it has now got very few electrons, and therefore, we said that this region is depleted of all mobile charges, okay. But what are the charges present here? We discussed that it is all the fixed ions due to the donor doping. The donor dopants have all ionized, and they all have their fixed positive charge that is sitting in here, okay. So, this is the condition, and we want to look at the electrostatics of this problem. So, when we introduced the concept of junctions, okay, we said that in order to study the electrostatics, we will need to solve the differential form of Gauss's law, which is something called as the Poisson's equation, okay. And that is exactly what we are going to do here. We are going to solve the Poisson's equation, which I have sort of rewritten out here, which says that, and this is the one dimensional Poisson equation, which says that dE by dx, where E is the electric field, okay. So I am calling it E, but it is actually the Greek alphabet psi, okay. So dE by dx is equal to rho by epsilon, where rho is the charge concentration per unit volume, okay, in the space in the region of the semiconductor in which we are trying to analyze electrostatics. So that is the charge concentration per unit volume. Epsilon s is the permittivity of the material, which in our case is the n type semiconductor that we are looking at. And for silicon the relative permittivity is of the order of 11, okay. Now in the depletion region we are going to make a very some might say drastic, but let us say it is an approximation which is something called as a full depletion approximation, okay. So the depletion approximation basically says that the charge concentration here. So what are the charges present in the depletion region, in this region? You have the fixed donor ions, okay, you have the positive charge. So you have plus Q into Nd per unit volume, okay. So these are all the ionized donor dopants. Then you have minus Q n, where n is the electron concentration, and plus Q p, okay. So that is the complete count of all the carriers or all the charges present in the in this region, the depletion region. And if we have counter doped this material, if you have added both Nd and Na and kept Nd to be greater than Na, we will also account for the ionized acceptors by writing minus Q Na. But here let us just keep it simple, let us say there is no counter doping, it is just these three components, okay. You do have holes, you do have electrons, and you do have donor dopants, but the electron count, you see the electron count at the interface, okay, is much smaller than the electron count in the bulk. So we had defined this region here, which is very far from the junction, as a bulk, okay, and the electron concentration of the bulk is approximately your Nd, which is the ionized donor dopants, and therefore your interface electron count is much less than Nd, and that is why we said this region is depleted. And P in a n type semiconductor is again very small, okay. So this is also small, and therefore we say that in the full depletion approximation we say that n and p are so small that they can be neglected, okay, and therefore the charge concentration per unit volume is simply Q and D, and therefore we replace the rho, which is the charge concentration per unit volume, with Q and D, and we rewrite our Poisson's equation as dE by dx is equal to Q and D by epsilon s. Now this is a very simple this is a simple differential equation to solve, and your electric field turns out to be varying linearly with distance. So that is what it tells us. The solution of Poisson's equation under the full depletion approximation says that the electric field varies linearly with distance, and there is an integration constant here, okay. Now how do we determine that constant, okay? We say that, see, what is the electric field? The electric field is there because there is a bending. You see, this bending is also the potential, right. So we are also we already defined we already said that your energies are essentially the Q times the potential, okay. So Q times the potential is equivalent to your energies, okay. So the band bending in the energy band bending, okay, I am sorry, the band bending of these energy levels is equivalent to the existence of a potential that varies with distance, okay. So the potential is varying with distance. So, the potential is a function of x, and therefore, there is an electric field. So, whenever you see a bent band, it means that there is an electric field in that region. So, very far from the junction, there is, once you cross this point, there is no more band bending. Okay. So, you had band bending to a certain extent, and then the band slowly flatten out, and then it is completely flat. And beyond this region, it looks like the semiconductor does not know about the existence of a junction at all. Okay. And everything here was the depletion region. Now, we define this width as the width of the depletion region and give it a symbol x subscript d. The d stands for the depletion width. And beyond this point, there is no band bending. So, any electric fields that exist in the material due to the formation of this junction is all existing between x equal to 0 and x equal to x d. Okay. And therefore, the electric field from this point onward, so the electric field from this point onward is 0, all right. So, that is the boundary condition that we are going to use. So, we are going to say that at x equal to x d, the electric field is 0, and of course, the electric field is 0 even for x greater than x d. Now, applying that boundary condition and using it, we can calculate this integration constant, and we find that the electric field, the expression for the electric field is given by this term here. Okay. So, the electric field is q n d by epsilon into x minus x d. So, let us look at this picture a little bit more carefully. Okay. So, let us look at this map. Okay. So, this is the, so I have drawn these two dotted lines to sort of mark out all the events in the depletion region. So, that is my x equal to 0, and that is my x equal to x d, and I have shown the x axis here. Okay. So, that line there is x equal to x 0 and that is x equal to x d. So, that is the width of the depletion region, which is x d. Now, all the band bending happens within this region, and beyond this the bands are all flat. Okay. And this was my depletion region. So, what are the charges? According to the full depletion approximation, the charge concentration in the depletion region is simply q times n d. It is constant because the doping is constant through the entire semiconductor. If the doping was varying with space, then this would vary, but right now it is a constant, and we are not considering electrons and holes, and therefore, which is basically the full depletion approximation, and therefore, that is not included into this picture. So, you have all the positive charges here, and these positive charges are balanced by negative charges in the metal, which forms a very fine sheet. So, this picture is very exaggerated. So, this sheet is going to be very, very thin. Okay. It is going to be a screen of electrons that balance out all the fields, and beyond this region there is no field in the metal, and beyond this region the bands are all flat and there is no field in the semiconductor. So, that is the situation, and we have calculated out the electric field to vary as q n d in by epsilon s into x minus x d. So, if you have to plot this electric field, so in the semiconductor, so again it is, this plot is there only in the semiconductor. So, we are looking at only the semiconductor at x equal to 0. So, if you were to take this expression here, at x equal to 0, the electric field is q n d by epsilon s x d with a negative sign. So, that is the electric field at x equal to 0, and at x equal to x d the electric field is 0, which was our boundary condition, and between these 2 points the electric field varies linearly with x. Okay. So, now how do we calculate the potential? So, what is the potential variation? The potential variation is essentially the, it is a measure of the band bending. So, if you can find the variation of the potential in the semiconductor with x, you have essentially found the nature of the variation of the conduction band bending with x, the nature of the variation of the valence band bending with x, etc. Okay. So, how do we calculate the potential variation? Now, the electric field is nothing but minus d phi by dx, okay. So, where phi is the potential, okay. And it is important, so although I have not shown it here, it is important to know how we have defined the potential, okay. So, this is the band bending, right. So, let us look at this as the distance x, that is the energies, and that is my conduction band, okay. So, we will just look at the conduction band. Now, we have to keep a reference for a potential. So, potential at any arbitrary point does not make any sense, it is with respect to a certain reference. So, we need to have a reference potential and then measure the different locations in x. So, phi at x1, phi at x2, etc., is all measured with respect to that reference. So, we will set that reference at this point. We will say that at x equal to 0 my potential is 0. So, that is my ground, okay, if you want to think of it that way, that is my measurement ground. And as we go into the semiconductor, this gap starts increasing and therefore, my potential starts increasing. Okay. So, that is my potential variation. So, that is the way we are going to define this phi, and the electric field is minus d phi by dx. Now, it need not be, I mean you are free to choose any reference you like, okay. So, for example, an equally valid reference is choosing the potential in the bulk as a reference. So, if this is the band bending, okay, and say that is x equal to xd, we could say that that is the reference potential, that is phi equal to 0, okay, no problem. As long as you apply the correct boundary conditions, it is absolutely no problem as to what you take as your reference potential, okay. But now for this analysis I have to choose one of these two, and I have chosen this as my choice of reference. So, at x equal to 0 my phi is 0, and I want to know what is phi of x, because if I know what is phi of x, I know the band bending, I know what is EC of x, okay, because EC of x is going to scale, okay, or it is going to be proportional to q times phi of x, okay, plus some offsets. So, since the electric field is minus d phi by dx, okay, so minus d phi by dx is equal to this term here, which was the electric field, which we obtained from solving Poisson's equation, and therefore, we solve this as the second differential equation, and we find that phi of x varies as the square of the distance, okay. So, it is a quadratic variation with distance, okay, plus an integration constant. Now, this integration constant really does not matter, because we are going to measure phi of x with reference to some other location, but then we could use that reference point to identify that constant, and we say that we have chosen our reference to be x equal to 0 is where phi is equal to 0. So, if you had chosen the reference to be different, okay, if we had chosen the reference to be phi equal to 0 at x equal to xd, then we will have a different integration constant. But now, since we have chosen this as our reference, we find that the potential, that is phi at xd, okay. So, this is my potential variation in space, okay. So, that is my phi of x, and x keeps increasing, and at this point we have your phi of xd, and beyond this the potential remains the same. So, phi of xd minus this point, that is the potential at this location minus this reference potential, is given by this term here, okay. And this has got a special meaning, it is something called as the built in potential of your device, okay, and we will denote this with a special symbol phi bi. So, bi stands for the built in potential, because from the edge of this junction till this point. So, from this point till this location here we have a potential difference of phi b I, okay. And phi b I is very nicely connected to x d, and x d, you can inverse this relation to obtain x d in terms of phi b I as the square root of 2 epsilon s phi b I by q n t. So, that is your depletion width. So, if you know the built in potential, you can calculate your depletion width, and on the other hand if you know your depletion width, you can calculate your built in potential. So, that is the straightforward, I mean that is the simplest analysis that one could do to determine the electrostatics of the Schottky contact, okay. So, it started off with the full depletion approximation, and we find that we get a reasonably good answer to what our depletion width is and how it depends upon phi b I. Now, all this is happening at thermal equilibrium. We have not applied any voltages. We have created the junction, left the device in the dark, and we find that this is the electrostatics. So, now let us say we decide not to make the full depletion approximation, okay. We want we are not happy with the full depletion approximation, we want to solve things a bit more accurately. How do we solve it, okay. So, let me just introduce it, and I will introduce the tools and the techniques to do it, and this is something that will be helpful even in the future, okay. So, let us again come back to this, a nice drawing here. I do not have to use my marker on this slide because it is all shown very neatly, and we have got a lot of labels on this drawing. So, this is the band bending. So, that is your constant Fermi level, okay. So, that is a Schottky contact, and you have your barrier here, okay. So, the Schottky barrier formation, and then that is your conduction band. The conduction band bends and then flattens out after some x equal to x d. So, that is the picture we are looking at, okay. So, let us just mark that point x equal to x d is somewhere there, and everything in the middle here is the depletion region. So, what are all these definitions, okay. So, that is the barrier height which is given by q phi b, okay. That is the potential that we had defined. So, that is our reference potential. So, phi is 0 at x equal to 0, this is my x coordinate, okay. So, that is x d, that is x equal to 0, my phi is 0 at x equal to 0, and this is the potential that is varying with space because of the bending. So, that is q phi of x, which we had identified to be a quadratic term under the assumption of the full depletion approximation. And this term here is the built in potential. So, this is your q of phi at x d, which is your q times the built in potential, which we found to vary as x d square. Now, since EC is varying with EF, in this region this gap here, okay, that is between the conduction band and the Fermi level, is essentially EC minus EF, or to be more accurate you can say EC is a function of x minus EF, okay. So, that EC minus EF term varies at this location. What is the EC minus EF? It is equal to q phi b, and at this location what is the EC minus EF? It is equal to whatever it is in the bulk. So, we define q phi b and the bulk EC minus EF. So, this is what the semiconductor had before the creation of the junction, okay. So, we give it a special symbol because everything in this region is the bulk region, and this is all the depletion region. So, the EC minus EF in the bulk is clearly identified by defining the subscript bulk there, okay, and the EC minus EF here is varying with in space, okay. So, once this picture is clear, it helps with a lot of the analysis. So, now let us say we want to do a more accurate study, okay. So, we will say that the Poisson's equation, okay, now I have written it directly in terms of the potential. So, the way this comes about is, let us say dE by dx is equal to rho by epsilon s, where rho is the charge concentration. Now, clearly since E is equal to minus d phi by dx, you have d square phi by dx square is equal to minus rho by epsilon s. So, you need to have a minus sign in place there. So, in the full depletion approximation we had said that despite the charges being qnd minus qn plus qp, in the full depletion approximation we had said that these two are negligible terms and we had gone ahead with just that. Okay. But now we want to do something a little bit more accurate. So, we will say that getting rid of n and p is not really necessary because we really do not know the numbers, particularly as you approach the bulk. Okay. So, over here it might be a great assumption to make, but as you start approaching the bulk it seems that it is quite logical to expect that the number of electrons keeps increasing, and therefore, if you are trying to perform an analysis in this region it is definitely not very advisable to get rid of the n term. Okay. So, what we are going to do is we are going to perform the study in a region of the depletion region, but closer to the bulk as compared to the interface. Okay. So, we need a more accurate Poisson's equation, and we say that although we could retain p, we say that p is negligible. Okay. But there is no need because we have no information, and in fact it actually makes the mathematics a bit more symmetrical if you keep the p, but just for the sake of an example I have not retained the p. So, we say that okay, the p is still negligible because an n type semiconductor, and in the depletion region as I approach the bulk I have this to be my charge carriers. Okay. So, that is my Poisson's equation. So, you have a negative sign because of the potential, you are using a potential term, but then you have q and d minus, these are the positive donor ions minus the electrons in the bulk. So, now how do we go about solving this? So, we need to identify, so this is a constant, this is not a problem, but this is not a constant, it depends upon the potential because it depends upon EC minus EF. Okay. So, let us identify n a bit more clearly, and I will just get rid of these marks here so that the slide is more clear. So, what is n? N is the effective density of states in the conduction band into e to the power minus EC minus EF by kT, and we know that in the depletion region EC minus EF is a function of x. Okay. So, what is, I need to represent EC minus EF as a function of the potential. I want to get everything in terms of the potential because the left hand side has got a potential term. I want to be able to construct a differential equation that I can solve. Okay. So, I do know, I can see that it is connected to the potential, but let me sort of make it very clear. So, what is EC minus EF? EC minus EF is nothing but Q times the barrier height minus the potential. So, think about it. So, this is EC minus EF, and that is the barrier height, and that is the definition of the potential. So, this minus that. Okay. So, 1 minus 2 gives you 3. So, that is exactly what we have written here. And what is the barrier height itself? The barrier height is connected to the bulk levels, right. The barrier height can be written as this plus this. So, let us call that 3 and 4. So, the barrier height, so 1 is equal, repeated 3. So, that is 1, 2, 3, and let us call that 4 and 5, 4 and 5. So, 1 is equal to 2 plus 3, I mean please do not take it as numbers. So, maybe I should say A, B and C, do forgive me for D and E. Okay. So, A is equal to B plus C, and A is also equal to D plus E. You could use either one of these definitions. Okay. Now, they just give you different, they give you a different picture. So, we could say that n is equal to nc e to the power minus ec minus ef, and we use this expression here and write n as this term here. So, what we are saying is the n at the interface. So, the expression for n at any location in the depletion region. Okay. So, if you say this is the depletion region and I want to get an expression for n at say some x, what we are saying is it is the n at the interface, that is n at x equal to 0 times e to the power q phi by kt, which means as phi increases n increases, which is expected because the interface has got very little n, and as phi keeps increasing n increases till it approaches the bulk concentration. So, now I can use this expression, okay. Or I could write another expression. I could say that I could go one step further. I can say that I want to define the interface term more clearly. So, I say that n is equal to nc e to the power q phi b by kt into e to the power q phi by kt, which is the same as that, and then I can rewrite the barrier height phi b in terms of the bulk ec minus ef and phi bi using this expression here. Okay. So, then if you look at this term nc into e to the power ec minus ef bulk by kt, what is that? That is basically the electron count in the semiconductor before the creation of the junction. So, that is what is going on in the bulk. So, that is the electron count in the bulk, which is approximately equal to your ND. Okay. So, this is another expression for n. You could use either of these expressions. Now, what we have done is we have taken this variable n and expressed it in terms of phi, which is the potential, and we have done that in order to solve this differential equation. Okay. So, we are just going through this example because it is quite I think it is quite illustrative with regards to the techniques we will use in future. Okay. It illustrates a lot of these techniques. So, now you have your n in terms of phi, we have n as a function of phi, and we make that substitution. Okay. So, that is my Poisson's equation. So, that is the equation I want to solve now to get a more accurate answer. Okay. And how do we solve this? Now, this looks like a tricky equation, right. You have a d square phi by dx square term on the left hand side, and you have got a function of phi on the right hand side. So, essentially you have got an equation which says d square y by dx square is some function of y. Okay. So, let us take a general equation like this. So, here is one trick that you will find is very useful in order to solve an equation of this kind, and simply what you do is you simply multiply dy by dx on both sides. Okay. Now, what is this term? This is nothing but the derivative of dy by dx whole square with respect to dx, because if you were to expand that, you will first differentiate this term and then you will take the second order derivative, that is exactly the same as this. So, that is your left hand side, and your right hand side is simply dy by dx. So, you can get rid of these dx, and now you have a very nice differential equation to solve. If you were to integrate both sides, you will end up with dy by dx square being equal to the integral of f of y dy. So, that is one, that is a technique to solve, and that is what we will be using. So, what we do here is we multiply both sides by 2 d phi by dx. So, you have that term that essentially gives you this term here, and that is equal to, now d phi by dx square is nothing but the square of the electric field, right. So, we now have an expression which says d electric field square is equal to all this term on the right hand side, okay, and you just integrate both sides. The left side will be the electric field square, and after you integrate the right hand side term, you will get some function of phi, and we now know the electric field to be the square root of that particular term. So, this is very much solvable, okay, and in fact, we will go ahead and solve it in great detail later on. Of course, From this point on, particularly this topic onwards, the course does get a bit mathematical in nature. There are going to be a lot of concepts to learn, but it is also important to learn how to calculate. So, we will go through a lot of derivations. It might appear quite painful to some students, but nevertheless it is my duty to go through all these derivations, okay, because so that you have an understanding as to where everything came from. But having said that, in your exams and in your examples, okay, we will not be quizzing you on how to derive a certain expression. So, that is not the point of the course. The point of this course is to sort of communicate certain concepts and quiz you on the concepts, and yet show you methods and techniques to calculate, and also show you how these tools came about. Okay. So, that is that is why we need to go through all these this bit of mathematics. It is to show you all the tools and the techniques and the methods to perform calculations. Okay. So, do bear with me if the mathematics gets a bit too dull. So, that is the electrostatics of the Schottky contact. Okay. We will not worry about the electrostatics anymore, and now what we will do is we will try to take the Schottky contact out of equilibrium and apply a bias voltage and start observing whether there are any currents. Okay. So, we are all still working on the Schottky contact. Okay. So, it is still, we looked at the electrostatics and now we are going to look at the current voltage characteristics. Okay.